All right, hello everyone, and welcome back to Physical Geology 1403. This is the beginning of Module 2. You just took your exam, or should have taken your exam on Module 1. If you have not yet, do it as soon as possible. The later it is, the more points are deducted. It's not like a lab, it's not like a discussion board where I'm a little loosey-goosey with it. Exams are heavier content, and it's how I keep track of how everyone is doing in the class. And if I don't get your exam 1 until like week 6, that doesn't really help give me a good idea of where you're at. So I do need those turned in as soon as possible, lest ye lose more credit. For my online students, that goes for you too. You had the same time span to take the exam as my in-person students. I gave everyone 4 days to take it. It opened on Thursday last week, closed technically, was supposed to close midnight on Sunday. Okay. Any questions or thoughts for us to start the day with today? Super Bowl is over. My Seahawks won. It was a crazy good defense game. I couldn't help but feel bad for that poor Patriots quarterback. 23-year-old, first time in the Super Bowl. What is he, the second youngest quarterback ever to get to the Super Bowl? He set a record for getting to the Super Bowl and then proceeded to set some pretty bad records in the Super Bowl. And I'm afraid those will probably follow him in his career. He's never going to forget it, that's for sure. I didn't notice Haley Steinfeld in any of the commercials.
I don't remember which one it was, but the main character was Josh Allen.
Name's familiar, but I don't.
Bills.
Okay, yeah, I don't follow football that closely. But yeah, most quarterback sacks in Super Bowl history. Woof, poor guy. But he's got a whole career ahead of him. Hopefully, people give him another chance. He seemed like a fairly good quarterback. The Seahawks just had a crazy good defense game. What else? Any other interesting stories, comments, questions? Are they doing okay? Because I don't think we had them here last week either on Thursday.
He was here late. He had a stomach bug last
All right, Ulani did show up late last time. Okay.
week.
Sure. I have something for us all to think about if you want. You guys know the stuff about like healing crystals and spiritual properties of crystals and things like that? You ever? Why do people say that crystals have those sort of properties? Their reasoning usually has something to do with the crystals give off something.
Adriel's gonna be late. We're gonna be fine.
Okay, thank you.
I don't know because they're crazy millennials.
Crazy millennials? It's not only millennials, although thank you for grouping me with those people.
Hey, I'm purely based off my sister.
Is she one of those crazy millennials? Okay, I am a millennial, but I'm not one of the crazy ones, I hope.
Trying to tell me about like my horoscope and my star signs.
Oh, she's all about the horoscopes. Well, next time she tries to convince you about crystals, you can pull this out on her, okay? Because what they'll usually say is something to the effect of they give off certain energies. Like this one helps you with concentration. This one helps you with health. This one helps you with yada yada. Which, if you believe in that sort of stuff, sure, fine, whatever. But here's the scientific kind of denunciation of that thought process. All forms of matter have an energy state. Okay? Things with a high energy state tend to be the least stable. Okay, so for example, things that are in a liquid form have a higher energy state than things that are in a solid form, right? That's why they can move and all their molecules can move around, stuff like that, right? Things that are in a crystalline state have the lowest energy state of anything else in the universe. Like, so when someone says, oh, here, take this crystal, it has great healing energy, you can tell them, actually, crystals have the lowest energy of anything in the universe. That's why minerals take so much longer to break down as opposed to other things. You and I will break down. Like if you put my body on a table and then a feldspar crystal on the table next to me, which one's going to break down first as time goes on? Me. I'm in a much higher energy state than that feldspar crystal is. It takes a lot more time for that thing to break down, right? That's why. So just an interesting little tidbit there to start the day off.
So do you believe that having a crystal on you brings you like luck or prosperity or anything?
Okay, so believing in luck, I mean, that's not just associated with crystals, right? Rabbit's feet. People have associated those with luck forever. Although I would contend it wasn't very lucky for the rabbit if its foot ended up around your neck, right? So, I mean, this is a sort of superstition that has been prevalent in society for as far back as people can probably remember. You had a certain thing when a certain thing happened, and you think that it was because of that certain thing. Everyone's got that crazy uncle who wears the same pair of socks whenever his team plays in the bowl game, right? Okay, that sort of stuff is under the umbrella of superstition. Okay, I don't think that there is anything scientific to it, but if it brings someone comfort to think so, I won't necessarily argue with them about it.
As a scientist, are you superstitious?
I am not what I would call superstitious, just a little stitious. Hey, badum-tsh guy. Where's my badum-tsh?
Oh,
You didn't even hear my joke.
I'm dying.
I said I'm not superstitious, I'm just a little stitious.
Oh, okay. I'm sorry. I was in the middle of
Trying
trying not to cough.
not to cough? Okay, you can cough in my class. I'm not weird like that anyway.
What?
I'm not going to mind if you cough in my class.
Oh.
Okay. Cool. But no, I don't really have anything that I wear for good luck. I've got stuff that I wear out of sentimentality. Like when I'm not wearing a shirt like this, I'll usually have my bracelets on. I've got a necklace or two that I like to wear whenever I want. But it's not out of superstition or good luck or anything like that. She touches the roof of her car when she goes through yellow. Right, and it's the same philosophy of people throwing salt over their shoulder whenever someone mentions the devil, right? It's yeah.
Every time she makes sourdough, she takes her flaky salt
over her shoulder. So some of these things can be pretty funny. There are some pretty funny superstitions out there. Yeah. I do, however, put superstitions and religions into separate categories. Okay, just so we can be clear on that. I'm far more willing to debate someone's superstitions than I am to dissuade them or debate any kind of religious belief. Those are two very different categories in my head. Okay, great. There's our interesting factoid for the day. Huh? Good way to start it off. All right, any questions about any content or anything before we jump in? We finished Module 1. We're starting Module 2, which is all about surficial processes. So we talked about the rock cycle and the different components of the rock cycle. Now we're talking about all the different processes and things that happen here on the surface. Module 3 is about Earth's internal processes in more depth. Okay?
How many modules are there?
3.
Okay.
Mm-hmm. Each one is consecutively half as long as the previous one. So Module 2, Module 1 was 4 weeks, the whole first half of the term. Module 2 is 2 weeks. Module 3 is 1 week. Okay? So it was 4, 2, 1. And that's 7 weeks, but when you take into account that we have a few days for exam review, typically, we normally would, but we missed a few days for, weather and holidays and stuff, then it all adds up to the 8 weeks. So ideally, what we end up with is the last day of class, or the last Tuesday of class for you guys in your section. We will have our final exam review in week 8, and then I'll have the exam open from that point forward. Okay, but we'll see if if the schedule lines up with what would be ideal. Okay. So Adriel's coming, but Ulani's not. Okay. Naomi, would you mind getting the door for me? Thank you very much. All right, so today we are talking about mass wasting, and running water, and groundwater. This one's a little bit on the longer side, which is not great because we're already starting half an hour late. We had technical issues with the laptop to begin with. But we're going to jump right in and have as much time left over for lab as we possibly can. All right? But please don't feel like we're on because we're kind of running a little later than we normally would, you can't ask questions. Always ask questions. Hopefully those of you who have taken the exam and realized where you were a little weaker in your notes and your understanding than you should have been, came back to school today with a greater understanding of how important asking questions is. If anything, I want more questions asked after that exam so you're even more prepared for the next one. All right? Which, by the way, is going to be in approximately 2 weeks because there's 4 lectures, including this one, between now and when you take that. All right, well, let's start off with our conversation about mass wasting by discussing gravity. What is gravity? It keeps us on the ground. But what is it? It's magic. Ooh.
Scientific magic.
Scientific magic. You know, many people believe that magic is simply science that we can't understand yet. What do you think a phone would have looked like to someone in the 1400s? Witchcraft. Yeah, exactly. What do you suppose someone who does something potentially magical looks like to us now? Would look like magic, right? Maybe all our magicians, or maybe some of the best magicians are actually aliens using better technology than we have. I don't know. Somebody get David Blaine in here. It's a conspiracy, yeah. Speaking of conspiracies, did you guys see the whole thing with Epstein?
It's not a conspiracy, it's true. It's not a file. Have you read the files?
No, I have not.
You shouldn't.
I'm not talking about the files. I'm talking to the fact that he's alive.
Oh, that?
Yeah.
I mean, I wouldn't be surprised.
I saw a thing saying that he is Andrew Jackson.
That would be crazy,
Facts.
actually.
Hold on, are we talking about 1800s President Andrew Jackson?
Have you seen the conspiracy that?
There's what?
Have you seen the conspiracy that they actually killed Biden and the president that we had wasn't Biden?
Okay, we're not going down this rabbit hole of other conspiracies, okay? I just happened to see if that's in the files, and I'm less inclined to believe in the files, right? I'm just commenting. I made a random passing comment on this thing that people think that Epstein is still alive.
I mean, he might be. I wouldn't be
No.
surprised.
No, I'm not gonna say no.
I doubt it's real, but
I highly
just a
doubt
crazy
that dude would
theory.
commit suicide, okay? I highly doubt that.
Okay. Well, I'm gonna bring it back to center now. Let's talk about gravity.
You put yourself in this.
I did. I made the comment. I should have known better.
it is really interesting watching all of it unfold.
I know.
Let me say this. At the Grammys, is his name Trevor Noah? No, Trevor-
That is a
Trevor Noah.
person, yes.
Yeah, he was the host of the Grammys, and he kept mentioning Trump and all this stuff that he's getting into and stuff. And so Trump made a tweet about like really dissing Trevor Noah, and I think he's only doing that defensively. Nobody gets that angry if they're in the right.
Oh, I think that's absolutely true.
You know?
About most things Trump does. Trump lashes out.
Yeah. 'Cause
However I feel about the man politically, he is a terrible person. Okay, but we're not going down that rabbit hole either.
What about the fact that we might have been eating human meat this entire time because there's not enough cows to keep up with how many McDonald's there are in the country?
We don't live in a Soylent Green world. I've seen our cow ranches and the buildings that keep them in. There are plenty of cows. There are plenty of cows. As a matter of fact, if you take the biomass of every domesticated animal on Earth, It's about 90, what was the statistic? 94% of all biomass on Earth is domesticated animals. When you take into account everyone's pets, all the domesticated birds, like chickens and stuff, turkeys, geese, all the domesticated cows and horses, cattle, anything that is domesticated, including domesticated plants like crops, okay? When you take all of that, it equals the vast majority of all biomass on Earth. Overwhelmingly more than the wild stuff that we have. Very interesting. Okay, gravity, guys, gravity. What is gravity? Lexi said it keeps us on the ground, sure, but what is it?
An invisible force that keeps us on the ground.
Invisible force. Okay, now we're getting more detailed. So a force is an act, okay? It is a thing in the universe that creates an effect, okay? What causes gravity then, if it is an invisible force that has an effect? That effect being, in this example, to keep us on the ground. So the sun is what's keeping us on Earth.
And what's keeping Earth as close to the sun as it is?
Okay, so gravity keeping the Earth close to the sun, check. But why? What's causing it? The sun keeping us on Earth, not really. Not at all, actually. We will talk about that. But first of all, what causes gravity, friends?
An object that's really large in mass.
Mass. That's the key word. Large, not so much. Mass, though. I mean, size and mass are often tied together, but not necessarily. You can have an object that is so high in mass that it has an enormous gravity, but is smaller than other objects around it. There are stars out there in the universe the size of our planet. They're just extremely compact. But all that mass piled into a small object still has a very, very strong gravity. But you're right, it absolutely is mass. The presence of mass is what dictates the strength of gravity. Okay, so what is gravity? It's a force that makes stuff fall. It makes stuff fall to us, right? This is gravity. Boom, it does that. What's causing it? The presence of mass. Come on now, keep up. Don't do this to me. Man, I just had this thing reformatted and everything. All right, here we go. Okay, so stuff falls because of gravity. Gravity exists because of the presence of mass. Well, wait. If gravity exists because of the presence of mass, why am I not being pulled towards Jose? Or sorry, Jared. Jose's my other class.
Oh. I doesn't even know who's in.
I teach 5 classes. Don't even.
That exists as part of the Earth.
Say that again?
Being pulled towards the core.
I'm being pulled towards the core?
Let's see. Who's the greater force?
Yeah. Why is it a greater force? Why is there a greater force than the pull of me to Jared? What is that greater force? It's all gravity. What has the greater mass nearby? Which is part of?
The core.
Which is part of?
The Earth.
The Earth. I am not being yanked towards any of you, and you're not being pulled towards me. I'm not being pulled towards that moon globe. I'm not being pulled towards those frogs or anything else in this room that has mass. Because there is an object of even greater mass exerting a greater gravitational pull overwhelming that, and that is our Earth. Okay, so we are being pulled towards the Earth. Our Earth is being pulled towards the sun. Our sun and our solar system in general is gravitationally drawn towards the center of our galaxy. It's like a nested hierarchy of gravitational pulls. Now, if I were in deep space, hundreds of millions of light years from the nearest source of other gravity, just me and this pen, yeah, this pen would orbit me because I am the greatest source of gravity. It would be pulled towards me, not the other way around. But we're not in that situation. We are here on Earth. So, here we are. We're on Earth. We have gravity. By the way, gravity, such a crazy concept. Mass. The mere presence of mass does something to space which causes objects to pull towards it. Think of it as like if you put a bowling ball on a sheet. This bowling ball kind of weighs down the center of the sheet, right? And anything that goes on the sheet rolls towards that bowling ball. This is essentially what mass does to space and, in a weird way, time. What do I mean by that? Now, this goes a little deeper than you need to know necessarily, but it's freaking cool, so I'm going to say it, okay? Huh? Okay. Okay. The further you get from a source of gravity, time has less of an effect. It also has to do with the speed of light. Okay? So when you're approaching a black hole, which is an object, the object of the highest gravitational pull we know of, when I say that, think about this. Our nearest black hole, the nearest one to us, has the mass equivalent of 500 million stars. The mass of 500 million of our own suns is in that black hole. So yeah, lots and lots of gravitational pull, which is why it sucks everything in. The gravity is so powerful, light can't even escape. Light gets pulled in. Something that isn't even a particle. Photons behave as both particles and waves. They kind of ride that line, but their mass is so inconsequential that it just travels through the universe and nothing can affect it except the gravity of black holes. That's how powerful it is, okay? The closer you are yanked to that black hole, and the speed of light slows down for you because light is being pulled in. A force more powerful than the speed of light is pulling you in. So, because light is slowing down for you, but not the rest of the universe, to your perspective, as you are slowly approaching that black hole, the rest of the universe goes faster and faster and faster and faster. The rest of the universe looking at you, you look like you're standing still. You look like you're not even moving. But as you look out at the rest of the universe, you see the whole life of the universe pass before you as you are slowly pulled into the center of that black hole. Time and space are affected by the presence of gravity. We've actually experimented with this. We took two identical twins. We kept one here on Earth and put the other one in space for a year. The one here on Earth, time had gone a little faster. Their cells had not aged at the exact same rate. They were born at the exact same moment, developed at the exact same time in the womb. They looked identical. But when after a year of experimentation, one of them was out of sync with the other because time had gone slower for them.
So the one in space, their cells were like dying faster or slower? Or not dying, I don't know the word.
Aging.
Yeah.
Right. Not necessarily dying. Right. You could, I suppose you could think of it like that. If you want to think of aging as just slow motion dying, it's kind of a depressing way to think about it.
It's the truth, John.
It's the truth. Why fight it?
You're an optimist and I'm a pessimist.
What can I say? I like to be an optimist. Okay, but we're spending a lot of time on this. Objects are pulled towards the greatest force of gravity in the area. Okay, so we're pulled towards the planet. Okay, so here's our planet. Whoop. Here is Naomi, hanging out in Odessa, Texas. Okay. Here is Cole. He's hanging out in China. Congratulations on your vacation. Okay. Naomi drops a pen. What direction does it fall? Down. Sure. Yeah. Cole drops a pen. What direction does it fall? Okay, so it's going to fall down too.
Not that way.
Oh, not that way?
Towards the core.
Wait, hold on. That was down.
Towards the center of mass.
Is this not down? Is this vector not down?
That one's
Oh, so you're telling me that down is just a matter of perspective? What? Nonsense. That's ridiculous, I say. So where are both pens falling towards then? Yeah, the center of mass, we call it. All objects on Earth are always 100% of the time being pulled towards the center of our planet. I really don't like gravity. It gets me down. But guy is failing again. Okay. Yeah, all objects being pulled towards there. Pens, rocks, everything. When rocks fall under the influence of gravity and gravity alone, we have a name for that. We call that mass wasting. I am not impressed with the behavior of this laptop after being formatted. There we go. All right. So, when gravity causes a rock to fall, mass wasting. So mass wasting is, well, I just said it. But what this has to do with is a couple of factors. For a rock to fall down under the influence of gravity, something must have changed in its environment. Because the gravity is always there, it's a constant. The gravity is always there as a constant, but the rock has not fallen previously. Something must have kept it from falling before. Some kind of support structure. So if my rock is now falling, what must have changed? Yeah, a change in the environment, which caused what? Removal of that support structure. What sort of changes in the environment can cause the removal of something like a support structure for a rock? Earthquake, sure. Weathering and erosion. Okay, which is why mass wasting was mentioned briefly in that lecture. Okay, so this brings up something called the angle of repose. The angle of repose is the maximum angle at which an object can be at rest without falling under the influence of gravity. What the heck does that mean? That was a lot of words. Well, do not worry. I have a practical demonstration. All right. The maximum angle at which an object can be at rest without falling under the influence of gravity. Here I have a plane, a surface. And upon that object, or upon that surface, an object. At some point, as I tilt this surface, that object is going to fall off of this surface. Are we confident of that? That angle is going to be the angle of repose for that material. Let's find out what that is, shall we? Move forward so it falls on the... There it is. This right here is the maximum angle at which that object can be at rest on this surface without falling under the influence of gravity. More than that angle, it falls off. That is the angle of repose. Now let's try it with another object. Kind of a different angle, huh? So, what can we interpret about what determines the angle of repose?
The shape of the object,
Why would the shape of the object matter?
because the marble was round, so that means it doesn't have
Okay. Yes. But what concept are you talking about here? When you're talking about it doesn't have as much, the marble, the sphere didn't have as much.
Less surface area.
There it is, surface area. The amount of surface area that is touching the surface in question is going to increase the amount of friction that holds it there. So this object with the flat sides had more surface area in contact than this marble that is spherical. So the shape is important, but also the material. What if this Lego is made of glass?
Is it still the same shape?
Still the same shape.
Should have the same angle, right?
It wouldn't. Glass has less friction than plastic does. So the type of material matters as well. Not as much as the shape, but it does matter. So the material in question and its shape will matter. Can you tell me under what circumstances I would have objects that are more rounded? What must have happened? You remember that concept? When we talked about sedimentary rocks and weathering? The more rounded my grains are, the more weathered they were. The more angular they are, aka the more surface area can be in contact with other things, the less weathered they were. Okay? So these are the things that dictate angle of repose. So for example, if I had a very fine-grained, spherical-grained sand, it would have a lower angle of repose than angular large pebbles, okay? The pile of sediment or rock or whatever the debris is will have an angle of repose only as high as it is capable of maintaining. If you dump more sediment on that pile to increase the angle, stuff's going to fall off the side of that pile until the angle of repose is reached. Why does that happen? Because all things in nature are seeking a state of stability. So my slope, following that logic, is going to make stuff fall off of it until that angle is reached. Okay? Give my slideshow a second to move on to the next slide here. All right. So, enter mass wasting. Rocks are falling. Rocks are falling under the influence of gravity. These rocks down here are tumbling down slope. There's no flowing water here. There's no wind that we can see. What caused it? The unending force of gravity finally won. Okay? And when you look, as those rocks reach the bottom, you'll notice there's a whole nother pile of rocks here at the bottom. Clearly, this slope is shedding material off of itself. Why would it do that? Why is stuff continuously falling off? Because this slope is gradually approaching the angle of repose. Once it reaches the angle of repose, stuff stops falling off of it. It's all at rest under the influence of gravity now. Okay? But it doesn't stay that way. Any of you guys here been to the Grand Canyon? You have? Yeah? Great. So from your recollection of the Grand Canyon, the sides of the Grand Canyon just kind of look like that, right? Just kind of like a straight up V shape. Yeah?
Not quite.
Not quite. Right? The Grand Canyon is doing this. That's what the sides look like. This is what the Grand Canyon looks like right here. Okay? You've got more slopey parts and more cliffy parts. Those are technical terms. Okay? Here we have like a cliff and a slope, and a cliff and a slope, and a cliff and a slope. I'm kind of in my way here. And a cliff and a slope and a cliff and a slope and a cliff all the way down there. Okay. Why is it doing that? Let's unpack that. Weathering had a different effect on different minerals. Minerals have properties. They respond to changes in environment in different ways as they seek stability. That means that the rocks they are part of will do the same thing. Now that we know that rocks have properties, because minerals have properties, it should not be a foreign concept to think that layers of rocks have properties too. One of which is angle of repose. The angle of repose for each different layer of rock is going to be different. This sandstone has a higher angle of repose than this shale, which has a lower angle of repose. Maybe that angle of repose is 70 degrees and this one is 30. So that's why we have these kind of alternating cliffs and slopes going down to the Colorado River here. Okay? We understanding that concept okay? Different angles of repose for different layers of rock.
But also, wouldn't it be like mechanical weathering has a different timeline?
Mechanical weathering is what is occurring to cause this. The angles of repose are found as processes of weathering are breaking the pieces of that slope off. Once, and that's going to keep happening. It's just that nothing's going to happen, nothing's going to fall purely under the influence of gravity once that angle of repose has been reached. Now, I mentioned a minute ago that the angle of repose does not always stay constant. What things can you think of that might change my angle of repose? Not really the wind. Wind could be a driving factor for the removal of sediment and debris and such, but that has nothing to do with mass wasting. What things can happen in nature that can change the angle of a slope? We're considering weathering to be independent of the angle of repose, as that has to do with mass wasting. Angle of repose has to do with mass wasting for this exercise. Now we're getting somewhere. What can that make?
Well, they can make the land rise and fall.
Right, so that's going to be a long-term change, the rise and fall due to tectonic forces. There are sudden changes that those tectonic forces can cause, though. That's long-term. It happens very slowly. What's a very sudden, shocking... What does an earthquake do to my slope? If my slope is doing this, where's my angle of repose? I don't know. Neither does the slope. Stuff's going to fall off my slope while this is happening. You know what we call this when stuff falls off my slope all at once? It's a landslide. It's what we typically refer to it as. There have been a whole bunch of really bad landslides in American history and world history especially. There are some really bad ones here. You can look up these landslides that happen in these places. I'll show you a couple of examples that happen here in the US in just a minute here. But an earthquake can change my angle of repose. What else can? If my angle of repose is right here while my sediment is dry, and then I saturate my sediment with water, what's going to happen to my angle of repose?
Isn't it going to increase?
Why?
Because the water's making the material more dense.
It's not making the... Well, okay, so it's adding mass, which is a factor. It's not really making it more dense, though. What's happening, though, is as you add a little bit of water, it... Yeah, it sticks to itself. Water is cohesive. That's why when you make a sand castle, you want your sand to be a little damp. What happens if you add too much water to your sand? Falls apart. You get a pile of wet sand. That's what happens to the other sediment too. Too much water, you remove the friction between your grains. They don't hold together. So instead of having this angle of repose, I'll have that angle of repose. And stuff's going to slide off of it until I reach that angle. Okay? Also, deforestation, industrialization. These are all things that cause mass wasting as well. Can you imagine how heavy a city weighs? Think about how many millions of tons of concrete and steel and glass and bridges and tunnels, people, water infrastructure, sewage infrastructure, power plants, electrical lines. Think about how heavy cities weigh. It's a heck of a lot. So when you put a city in a place that doesn't have the most stable sediment, the most stable angle of repose, then yeah, you risk landslides, carrying away pieces of your towns, of your cities. Deforestation, that removes the root structures that hold that sediment together. Remember when we learned about soils? We talked about what happens to the soil when you cut down pieces of a rainforest, right? It gets carried away. Okay, so removal of plant material can increase the likelihood of mass wasting. Here's an example, La Conchita, California in 2005. They experienced a period of heavy rainfall, not typical for California, for those of you who are not familiar with California. Okay, we still haven't gotten any rain today. Like they said, it was like 88% chance of rain.
That's raining. Not hard, but it was like, there's water coming from the sky.
I didn't see any of it.
I had to use my electric bubbles getting home.
When were you on the road?
9:21.
I was already in here. But I walked out of the gym at like 9:05, and then I got to my office at like 9:10. There was no rain. I missed a little bit of it. But anyway, this landslide collapsed down into this community, killing people, destroying houses, etc. This is Oso, Washington. When I lived in that little town, I told you I lived in that town not far from Mount Rainier called Ording, right? Where they did the Lahar drills and such. This town is just further down the road. I remember this day vividly. I was just walking down the road. There had been some heavy rainfall, and again, this is Seattle, so rain is not uncommon in Seattle, but there had been like 3 days of heavy rain without stopping, which is not typical, okay? So I remember just walking down the road, and all of a sudden, my nice, quiet little town of Ording was erupting with sirens and people getting in cars and everyone driving down the road. Felt like everybody was leaving Ording. I was like, what the heck is going on right now? That rainfall here in Oso had caused this escarpment to become unstable, saturated all those layers of rock and soil, and caused it all to collapse. It collapsed down into this river, mixed with that water, and more or less tsunamied through this community. Everywhere you see that is red is a home or business in this community. This is what Oso looked like afterward. 43 people were killed here. This is the deadliest landslide in modern U.S. history, as far as we've been recording it. There have been worse ones worldwide, for sure. But since we've been paying attention, this is the worst one in U.S. history. Everywhere you saw where those red dots were, they aren't there anymore. So it's pretty important that we pay attention to the sort of conditions that could lead to this thing happening, right? Mass wasting is not a joke. People's lives are on the line. So how do we watch for this? Well, we can take something called a GIS program. You guys know what GIS programs are? Geographic Information Systems. Most jobs will utilize it anymore these days. It's not just a geological or geographical feature anymore. Cities use GIS systems. Large companies will use GIS systems for analysis. Okay, if you need any kind of analysis on demographics of people or of geography or of maybe even just for sales, tracking sales across a region, GIS can help with that. So how do you use it? Well, you take a map of the US and then you input into this program a data sheet, like an Excel spreadsheet with, let's say, rainfall across the United States greater than X amount of rainfall, okay? So anything more than, say, 2 inches over a certain period of time, okay, which could saturate soil. Then you put that in the system and you say, color code all those regions of the US. Okay, great. Then you can say, input all of the mountains in there. Why would we be interested in mountains, by the way? Huh? Yeah, but why? Why would mountains have to do with this, mass wasting? Why? There needs to be an angle. Is this pen sitting there on this table ever going to fall off the table under any influence? No. But if the pen is right there and its support structure removes itself, there it is. You have to have elevation for stuff to fall down from, right? So mountain ranges. So you take all the mountain ranges in the US and you put them into that map and you color code it. Okay, great. Then you take all the places that have running water. Why would running water be a factor here? Like rivers and streams. Erosion. It can provide weathering, but more than anything, it's removing material, right? It is breaking down and removing material, support structures in particular. So you take those factors, you put them all in Excel spreadsheet form into this program, you have it color code all the parts of the US that all of that data lines up with, and then you say, show me all the locations where all this data is in the same place. And then you color code it according to how severe those different conditions are. Highest elevation, steepest slopes, most rainfall, most running water. And you make something like this, where everything that is red has a very high potential of mass wasting, and everywhere that is beige has a very low potential. As you can see, the Appalachians can be a little dangerous. As you can see, where we are is a lot of trouble. We have high potential of mass wasting, right? No. We lack mountains, we lack heavy rainfall, and we lack running water.
I can see where the yellow is. I think that's where my husband's from.
Right there?
I think that's more for the Alpine area.
Yeah, it is.
Yeah.
Yeah, they have some elevation over there.
It's very pretty though.
Definitely. Yeah. There you go. This is how you can use something like a GIS program. Now, you can go to the US Geological Survey website, and they have programs like, they have printouts, maps like this of every possibility of any natural disaster in the US. And I would highly recommend, before you pick up and move somewhere, or you buy a house, go and look at that stuff. Before moving to West Virginia, think, I'm going to go and look at the landslide potential of this part of West Virginia I want to live in.
I just wouldn't move to a state that's mostly covered in all the colors.
Well, I mean, all these states have their virtues, right? I've been to every state in the US except Alabama. No particular reason. I just have never made it there, which is a shame because I lived in Louisiana for 2 years. And now I live in Texas, and I still haven't made it to Alabama, right? Yeah, okay. I never made the trip. Anyways, all states are beautiful for one reason or another, okay? But yeah, some of them have more dangers than others, and it pays off, especially if you're looking to be something like a homeowner or a business owner in that area, to know what those dangers might be. You better believe the insurance companies look at that stuff. Okay? All right, so when we have these landslides, which is the word I've been using, but I'm going to call them mass wasting events right now, we classify them using a couple of different ways. The first part of that word, saying the word landslide, land, let's talk about where that comes from. The first part of that name comes from what the material in question is. So if we're looking at unconsolidated stuff, random bits of clutter and rocks and whatnot, it'll be a debris something. Or if it's mostly mud, it'll be a mud something. It could be a rock something if it's just solid rock that's tumbling down, okay? The second part, that slide part I was talking about, there's a couple of different options. There are falls, which means it's just free falling through the air.
Like a waterfall.
Yeah, exactly, like a waterfall. So a rock fall is literally when a rock tumbles off a cliff, free falls through the air and hits the ground. That is a rock fall. Okay? Then you have slides, where there are zones of weakness in my layers of rock or sediment, as the case may be, and stuff travels over that plane, over that zone of weakness. Okay? So there are two types of slides, rotational and translational. Translational typically happens when you have just solid rock. You have one layer of rock that slides over a second layer of rock. Usually, there's a buildup of water that happens between these two and reduces the friction between the two layers. That's why that happens, okay? But a section of this layer, this top layer, is going to detach and fall downhill over that plane. In a rotational slide, this usually happens whenever you have very kind of broken rock, kind of shattered rock, or a lot of sediment, okay? It gets saturated, and the top part kind of collapses down, compressing the sediment underneath of it. As that becomes more and more compressed, it can't really compress anymore, and so my sediment that collapsed down on top of it kind of gets shoved out, scoops itself out, and down onto the slope. So you get this rotation of down and then out. This is a rotational slide. You can usually tell if it's a rotational slide because it makes these sort of step blocks, okay, as it's compressing down on itself down below. And then we have flows. A flow is when there is so much energy or water involved that it behaves as a fluid. Have you guys ever seen videos of what people do when they take like flour, a very fine-grained powder, and then they pass air through it? You ever seen those videos? It looks like boiling water. The flour looks like boiling water. They have added so much air and energy to it that it's behaving as a fluid. The same sort of thing can happen in a flow. You can also get a flow when you add a significant amount of water. Now, water is not the driving factor. Gravity is. There just happens to be water there. We already talked about a certain type of debris flow in this class, lahars. A lahar occurs when the volcano heats up, the glaciers melt, all that ice travels, melted ice, it's water now, travels downhill, picks up a bunch of debris, and carries it down through the stream, okay? That is a flow, a debris flow. Okay, so we have debris, mud, and rock, and falls, slides, and flows. And that collectively can make the name we give our event. So you can have a rock fall, you can have a mud slide, you can have a debris slide or a debris fall. Any of those things can mix together to describe what happens, okay? So let's talk about the different examples of these things as they occur commonly in nature. Slumps. A slump is a type of rotational slide. So you can see that kind of stepping pattern here, okay, to this event. What do you suppose caused this slump in this picture? What were some contributing factors we can identify by looking at this picture? What could have contributed to the collapse of this? That was actually a decent Yo Mama joke, actually. Yo Mama's so fat, she caused a landslide.
Oh.
She sat down for the picnic and the mountain collapsed.
I don't know, there's not like a lot of resources going on with that.
All right, there's not a whole lot of vegetation, but clearly this effect happened below the level that the vegetation could have. Where?
It's on a beach, isn't it?
Yeah, that's running water, beach, river, whatever it is. Running water means transport of sediment. We are removing material from the bottom of this cliff face. That's absolutely a contributing factor here.
So high tide was a factor.
Well, again, whether or not, I agree, this looks more like a beach than anything, but even if this was a river, it's removing material from down there, okay? Add to the fact, what if there was some heavy rain? So you're removing support from down here while adding weight and removing friction in the sediment up here by adding water. What's going to happen? You're going to get a slump, okay? Then we have rock slides. This is a translational slide. This happens when you have layers of rock that are parallel, right? Because all layers, remember the principle of original horizontality, all layers of sediment are deposited horizontally. They get turned into rock, and then that rock can get tilted or folded, right? So they are tilted at an angle, but something causes one layer to slide down off another, okay? Like this. That is a rock slide. It's falling off the layer underneath of it. Chunks of rock are. Now, this can happen in places where you get an engineer who never bothered consulting a geologist. Okay? Have you ever driven through California, like Northern California or Nevada, Oregon, even the Rocky Mountains in some places? No? You've never seen where they've stretched big, thick metal nets across a whole mountainside across a road? You've seen this? You know why they do that? Stop falling rocks. Why are the rocks falling in the first place? Why are rock falls such a problem? Because some dumb engineer decided to build their road right here on a slope where the layers of rock are parallel to where your road is. Translational rock slides are a big problem in that situation. All you have to do is put a little more work into it and find another way to cut through where your layers of rock go like that. Problem solved. This happens when engineers don't bother consulting geologists first. So you have to spend literally hundreds of millions of dollars to stretch netting across this whole mountainside to keep rocks from falling, and it doesn't even stop all the rocks.
There's this one rock on the way to my husband's hometown that's just almost perfectly round, just sitting on like a cliff area.
Mm-hmm.
And every time we pass it, I look at it, I'm like, one day it's gonna be our day.
Yep.
It feels very Final Destination.
You'll drive past it for 20 years, and then finally in the 21st year, it will fall and destroy your car. Yeah. I mean, that's possible. Every year that passes, more and more of its support gets removed. Why don't you just go up and push it down?
I know.
Just make the hike. Save your life in the future.
Or make all of his stupid friends do it.
All right.
That's something they'd be up to.
Well, if you don't come back from spring break, I'll know what happened.
I'm moving during spring.
Okay.
Anywhere.
Probably a good idea. All right. Now, I just want to say, I know it sounds like I'm ratting on engineers a lot. Engineers and geologists poke at each other all the time. But I fully acknowledge the need for engineers, okay? And I respect engineers for the work that they do. Just got to put that out there.
How much is that your equivalent of Sheldon's geologist?
No. Sheldon despises and makes fun of geologists way more than I ever do about engineers. Geologists and other scientists are, we tend to be the theorists and academists. Engineers, we fully acknowledge, practically apply the things that we come up with. So I can say something like, if I were a physicist, I could say, these are the constants for gravity as you approach a black hole. That's all I can do. Engineers are the ones that have to build the machines that can travel as close to a black hole as they can while staying within the boundaries that I have determined. I can't make the machines. I only stay within the realm of theory until an engineer brings it to life. So I absolutely acknowledge the need for engineers and fully respect engineers. We poke at each other. Okay. This is an illustration from a place called Gravant, Wyoming, by the way. I've been there. It's very impressive. A whole, I want to say like 6 kilometer section of this mountainside, this valley side, I should say, collapsed, fell down a further 6 or 7 kilometers into this valley, and filled it in and created a lake. What happened here? This was a layer of sandstone underlain by a layer of clay. So the sandstone gradually filled up with water from rainfall, but that water could not percolate down into the clay. And so the sandstone got super saturated, reduced the friction between the 2 layers of rock, and the sandstone went whoop downhill. Can you imagine how loud that must have been in that valley when this happened? We're talking about kilometers of rock falling down this valley side and filling it in. Incredibly loud must have been. Okay. A debris flow. I already mentioned an example of this. A lahar is a great example of this, okay? So lahars and other debris flows, they travel very quickly downhill, picking up anything in their path. But as soon as they reach the bottom, they lose their energy and they dump everything else out wherever the energy was lost, okay? We call that dumped out material, we call that alluvium, okay? And it will make an alluvial fan. This kind of fan shape. An alluvial fan, we call that. Earth flows. These are very slow motion. This is what happens when you have a very humid area where your soil is pretty well saturated, not to the point where it becomes mud and becomes a mudslide, but it is so wet that it is still kind of, how do I put this?
Like kinetic sand?
More or less oozing downhill. Okay, slow motion downhill transport. This might have taken a decade or two to make it that far. But you can see this sediment, this soil, has gradually made its way downhill like a slow motion earth tidal wave almost. Okay, making its way downhill here. This happens in places where it's naturally very humid and they get a lot of consistent, though not super heavy rainfall. Places like Scotland, Ireland, and high northern places like that, but not too far north so that it turns into snow most of the time, but still a lot of rainfall. Okay. Then you have creeps. Take my word for it, ladies. Creeps are everywhere. This is your 3rd strike. No more but
Oh.
You should be listening to me. Okay. Where'd my pen go? I left it over there.
All right, buddy. You know what? Friendship off.
No! Okay. So, a creep is what happens when the top layers of soil freeze and thaw and freeze and thaw and freeze and thaw and freeze and thaw. Why would that make a difference? Well, let's say that I have some angle to my slope here. Okay. And my water in that soil freezes. What direction is it going to freeze in? Water freezing forms a crystalline structure, correct? It's going to form that crystalline structure at 90 degrees to the surface it's sitting on, which is going to be 90 degrees to the angle of that slope. But when it melts from that crystalline structure back into water, what direction is it being pulled in?
No? 45? 180? 360?
Whatever straight towards the center of our planet is. Because of what? Gravity. So it's going to make an ice crystal at that angle, but then melt at that angle straight down towards the center of the planet. So as this happens, freeze thaw after freeze thaw, you get this kind of freeze up, melt down hill motion of my soil. But what if I built a sidewalk on top of that soil? Or a street, or a curb, or a fence, or a gate? or a house foundation, it's going to get carried with it. Which is why you'll often see things like this. Look at this curb. This is in 1971. This curb and that curb are kind of offset by about a couple inches. 1974, here's a much bigger close-up. There's only a few inches of overlap left, right? 1993, the year I was born, they aren't even touching anymore. 2005, there's about 3 inches of separation between them now. What is causing this to happen? The soil underneath of this street has a creep where it is slowly moving downhill as freezing and thawing occurs year after year after year after year. And it's taking that curb with it. Okay, so if you were ever driving down, you'd be like, that's a really weird thing for that fence to be doing. That's a creep. Okay? If you're walking down the street and you notice that your sidewalk kind of takes this weird deviation for a couple of steps and then curves back around this way for no reason whatsoever, it's a creep. If there's a dude staring through your window in the middle of the night, it's a...
Stalker.
Thank you, it's a stalker. Okay? Okay. The last type is called solifluction. This happens whenever you have somewhere like up in the high north or far south where you have this phenomenon called permafrost. Have you heard of permafrost? Huh? Kinda? What is permafrost?
I've heard the word.
For the word. Okay, permafrost is where the conditions year-round are so cold that your soil is frozen. And only during the warmest parts of the month are the top few inches of soil where the sun is directly contacting, is it ever not frozen. A few inches below, still frozen, that's called permafrost. Also in places where you've got lots of compacted clays close to the surface. So what happens here is the top few layers of soil get saturated with water because the water cannot sink any lower than those top few inches of soil. And so that soil, saturated with water, flows over that harder surface downhill. Okay? So this is up in the northern Alaska during the summer. Lots of permafrost, top few inches of soil, unfrozen, but it kind of looks like waves of soil moving downhill. Okay, flowing on top of that permafrost down below it. Any questions about mass wasting? No? Not yet. Well, then let's talk about running water. All of the water on Earth, 97.2% of it is salt water in the ocean. The remaining 2.8%, 2.15% of that is glaciers, frozen. Of the remaining 0.65%, 0.62% is groundwater. That leaves 0.03% of all water on Earth as running water. 0.03%. Does that put a little bit into perspective for you for how incredibly rare fresh water is? How much of a resource it should be to protect? We need that stuff, right? Did you know that there are entire countries that have 0 sources of running water in them? They get all of their water from the ground or from taking it by essentially evaporating salt water so that and then scraping away the salts and you're left with fresh water. The nation of Qatar has no running fresh water in it. They get all their water from wells or from evaporation of salt water. We call that desalination. Okay? More and more countries are needing to go towards that as our sources of fresh water become either more polluted or overused. Okay, we'll talk about that more towards the end of the class today. But here's our general water cycle. Evaporation, most evaporation comes from the ocean. Why? Well, because 97.2% of all water is in the ocean, right? Evaporation, precipitation gets collected on the surface and then it runs off. This surface, where that collection occurs, lakes, rivers, streams, are sources of running water. Okay? Some of that does make its way into the groundwater as well. That's our groundwater, okay? Can we have a cool little side tangent about water real quick? Do you know how small a particle of water is? What is water? Someone give me the chemical equation for water. H2O. 2 hydrogens, 1 oxygen. H2O. Do you know how small each molecule of water is? If I took, smaller than an atom, no, it's made out of 3 atoms, 2 hydrogens and an oxygen, right? So it's the size of 3 atoms, actually. But if I took a cup, say one of these, and I filled it with water, the number of water molecules in my 1 cup is greater than the number of cups of water in the ocean. That's how small this stuff is. Man, isn't that cool, crazy to think about? Which means, statistically speaking, if that's true, and we assume that all cups of water in the ocean have at least 1 molecule in it from every other cup of water that has ever been taken out of the ocean or out of a river or a lake, then every time I take a drink of water, statistically speaking, I'm drinking at least 1 molecule that George Washington drank. Or whoever your favorite celebrity is. Statistically speaking, it's possible. Interesting, huh? Yeah? No? Did I lose you guys on that one?
No, I mean, I've always understood that we can't really retain or lose more water on Earth. Or from my understanding.
So, matter changes all the time. So, water can break down into hydrogen and oxygen. We do that artificially through a process called electrolysis. It's actually the principle behind things like hydrogen cell batteries, the principle behind things like rocket fuel. Do you know that rocket fuel is essentially just compressed hydrogen, compressed oxygen that you combine together, creates an exothermic reaction, and creates water as a byproduct? Right, so, which is it's kind of similar to how hydrogen cells work as well. But matter and energy interchange a lot, okay? And matter changes into other types of matter a lot as well. So it's not strictly true. Water can never not be water. But what happens when all our fresh water goes in the ocean? Or when we drink it and it becomes pee? You know, it takes a long time for that water to make its way back through the cycle to where we can utilize it again, which is why it's an issue, okay? All right. Because we care so much about where our water comes from and where it goes, we separate our continental areas into what we call drainage basins. A drainage basin is essentially an area designated as a place where water can flow through. So like right here in this mountainous area, every drop of water that falls to the right of that ridge and every drop of water that falls to the left of that ridge falls within this area and collects and flows out of it. We would call that a drainage basin, okay? So here are a few actual examples of drainage basins. The Mississippi River Drainage Basin takes up about half of the U.S. every drop of water that flows within this basin ultimately makes it out through Louisiana and the Mississippi River into the Gulf of Mexico. We can break that down into further smaller pieces. Missouri River, Ohio River, etc. We can break each one of those down into smaller pieces. This is the Yellowstone River Drainage Basin, which is a subset of the Missouri River Drainage Basin. Okay, so we break it down into smaller and smaller pieces, and we monitor the water that flows through each because we care so much about where it goes and how pure it is for our usage purposes. Okay. If any of you guys ever walked out into the middle of a stream or a river? Yeah, okay, Lexi. So as you're walking out into that stream, what happens the further out you go? What happens to the energy? Or think the velocity of your water. How about that?
I guess it's faster towards the center.
Yeah, it gets faster towards the center. Why does this happen? Why does it get faster towards the center? Open question.
That's where the stronger current is, I guess.
I mean, that's basically taking my question, turning it around, and then using it as an answer. It's not really explaining why. Doesn't really have to do with gravity.
Maximum velocity.
Yes, but why is that where there's the maximum velocity?
The science says so.
Science says so, yes. The science committee has deemed it thusly. No, there's a reason. Cole, any ideas? Why would the water in a stream be faster in the middle of the stream instead of on the sides or the bottom?
It wouldn't have anything to do with the shores, would it?
What do you mean?
Like with the fact that it's like I move, I don't. Like,
I like where your head's going. Keep walking through it.
is it because there's more water like towards the middle, and as you go to the shore, it kind of gets less and less?
Okay, so it's true that there's more in the middle. That is absolutely true. But why is the velocity on the sides less than that of the water in the middle?
More room to move.
Maybe on the side there are rocks.
Yeah, and what's it doing with the stuff on the sides? You say that there's rocks and stuff there. That's so true, but why does that make a difference? You're absolutely correct, but I want to know why. Yeah, the water's running into the stuff on the sides. There's stuff on the sides and bottom that's absorbing the energy, reducing the velocity of the water that's there. You know what's not in the middle of my stream? Rocks and tree branches and all that stuff, so it's free to move as quickly as it can. So yes, this is why we have this phenomenon where the water flows faster in the middle of my stream. Okay, well that makes sense for when I have, straight streams. But what about in a situation where I've got one of these? We've all seen these, right? These sort of meandering rivers, that's what we call these. So sure, where we have this straight stream section between curves, the water velocity is fastest there in the middle. But what about these curves? Where's the fastest velocity on these curves? The deepest area? Okay, well, where's that?
Could be outside, like, because I'm assuming the water is going straight, it's the edge, and then it turns.
Okay, so what you're saying is it's going straight, runs into that wall, bounces off of it, and then goes that way?
Yes.
Can you think of any scientific reasoning to justify that?
Maybe that's how it started, like the elevation when the river was forming.
It doesn't really have anything to do with elevation. These sort of rivers, meandering streams like this, they will actually happen in low elevation areas where you have very little slope. Cole is absolutely right, by the way. Just wanted to push it a little further, see if we could get there. To imagine this, you're driving down the road, okay? 35, 40 miles an hour, listening to your music, not really paying attention, and, oh, that's my turn! Okay, so you take this hard right, barely slowing down at all. Your car turns right, your body goes left?
Yeah.
Does it though? You're going that way. Now your car is going that way. Is your body a piece of your car? No.
Oh, your body is stable with that.
It's just an object inside the car. As far as your body is concerned, it should still be going that way. And that's where its momentum is going until it catches up with the new momentum of the direction of your car. So it feels like your body's going left as your car's turning right, but your body's actually still just going in the same direction that it wanted to before, that it had momentum for before. Yeah, well, not consciously, but physics is doing that. Your stream is doing that too. Cole's right. So it's going to keep moving forward. It's going to encounter that edge, have to run along that edge until it restabilizes there. And then it's going to run into that edge, run along that edge until it goes back to the middle or outside of that curve. Okay. So what does this mean? The highest energy, the most velocity is on the outer edge of these curves. What's that going to do to the material out there? We're going to weather and erode it. So the outer edges of these curves are constantly pushing out. So if that's where my highest energy is in my stream, where's the lowest energy in my stream then? Huh?
The opposite side?
The opposite side of the curve? Yeah. So while this is where material is being removed because that's the zone of highest energy, over here on the inside of my curve is the lowest energy, and that's where deposition occurs. Exactly.
You know, Josh, I find this analogy really interesting, knowing that I have a test today. So,
Yes.
yeah.
Isn't that interesting that I chose that as an example?
So
Good. Yes.
Saying I'm a bad driver?
No, I don't know that. Emma's taking her driver's test today, so everyone wish her good luck. All right.
Girl, it took me 3 times.
3 times.
Oh.
She doesn't want to hear that.
Hey, I also know somebody who didn't have to take the test at all.
Well, I mean, that depends on the state you're in. So I got my driver's permit in Virginia, and there they require you to have a permit for 6 months and take 12 hours of classes. So I got that, and then right before I finished my 6 months so I could get a Virginia driver's license, we moved to Ohio, and they don't recognize the Virginia driver's permit or the requirements. So I had to have an Ohio permit for 3 months and do all of their classes before I could get an Ohio permit. So,
My friend got his permit in like New Mexico, and so when he was getting it changed, they gave him a license instead.
Oh.
So it was just a mix-up.
Okay.
ladies and gentlemen, the Texas driving system. That was New Mexico, you said, right?
Yeah.
Oh, New Mexico is not better.
Ever since I found out that in 2025 they made it where parallel parking isn't required, I think I'll be okay.
What?
Oh, to test for parallel parking?
Yeah, they made it
What?
not required.
Yeah, I'm not parking street side anymore, guys.
I mean, they can like say, like they can tell you if they want to, but they don't have to anymore. Which I'm glad because no one does it anyway.
I mean, depends on where you are.
I would rather.
You go to a big city and you don't parallel park, you're not parking
I know,
anywhere.
I'd rather drive a whole mile down the street just to find not parallel parking.
Actually, I have had to use parallel parking whenever I've had to like go visit somebody at the hospital in my hometown because there's like street side parking.
Yeah, street side parking is rough if you don't know how to parallel. Okay. Okay, so I have a little model here that a colleague of mine on LinkedIn let me use for my classes. Okay, so he's a sedimentary geologist. He studies stream flows and the sediment deposition that comes from the flow of streams. Okay, so he put this together. This shows you how a meandering stream moves out. So notice how it's going to build, it's going to chip away, remove material on the outer edge of the curves, deposit it on the inner edge of the curves. But all the while this is happening, more and more material is flowing away downstream, eroding downstream. So it's going to carve out a valley as time goes on. Okay? Also, you're going to notice that eventually those curves, those river curves, go out so far that they reach a point where they just abandon that stream and snap back towards the middle. Because rivers are lazy. They're going to do things that require the least amount of energy possible. That's just nature. Okay? Animals generally veer towards that. People generally veer towards that. If I gave you an option between doing something that requires a lot of energy and doing something that requires very little energy that yields the same result, which one would you do? The low energy one. That's just how nature goes, right? So eventually, it builds it out so far that it costs too much energy to go all the way out there and back, and so it snaps the river back towards the center course, and that's where it's going to start flowing again. So watch this. Okay, so our stream is flowing out, and then it's going to start snapping back towards the middle. Hello? Gotta say, so far I'm not impressed with the reformatting that they did for my laptop here. Okay, watch how it builds out and then snaps back towards the middle. All the while carving out a stream valley. And look, you can see where it's depositing the layers of sediment. And then chewing away from those old layers of sediment and depositing new layers of sediment wherever the river currently is flowing. And there's our stream valley. Right? So, all of this material that's being carried away downstream, okay, we call that load. It's one kind of load or another, okay? We have dissolved load, which is everything that has been chemically weathered, okay, so dissolved into that water. A lot of that will actually make its way into the groundwater system. Then we have suspended load, which is all the material that is being carried in the water itself. Kind of gives it that murky, muddy sort of look. Okay? Then you have bed load, which is everything that's getting pushed along on the bottom of your stream or your river. Okay? The stuff that's too heavy to be in the water itself. But whenever your stream or your river reaches its dead end, wherever it is losing its energy at the bottom of whatever hill it's flowing down, it's going to drop all of that sediment. Do you remember the name for what we call it when that happens? What do we call all that stuff that gets dumped out?
What, Josh?
What do we call the sediment when it gets dumped out at the bottom of a river or a stream?
Oh, I thought you were staring at me. I don't have my glasses
No.
on, so I thought you were looking at me, and I was like, what, Josh?
No, I'm staring at the class in general.
Okay, what do you call it when what?
When all of the sediment gets dumped out at the base of a stream or river. We already talked about it today.
I know.
I may have even been kind enough, cool enough even, to have put it on the slide.
I don't even. Bed load?
No.
Erosion?
No. You're wearing glasses.
Alluvium.
It's alluvium.
Oh, alluvium.
Yes, alluvium is what we call all of the material that gets dumped out at the base of a river or stream. Remember, when it's on land, it's called an alluvial fan. We already talked about that. But when it happens out in the water, we call it a delta. Okay? A delta, like what's here at the bottom of Louisiana. The whole bottom half of Louisiana is just delta built on delta built on delta, as the Mississippi River is dumping out all the sediment that's traveled all the way down the Mississippi River from the Mississippi River drainage basin. And it's built its way out all the way into the Gulf of Mexico, and this is where it's currently building. This is its current delta that it is building up right now. All of this landmass was built up by all the sediment that it carried down after all these millions of years. So as our water from the Mississippi River hits the Gulf of Mexico water, what happens to our energy? It gets dispersed, energy is lost, sediment falls out, you build your delta. An alluvial fan is what we call it when that happens here at the base of a mountain. water comes down here, loses its energy as it reaches this flat area, dumps all that sediment out, adds to this alluvial fan. A levee is what we call it when a river floods, causing a whole bunch of sediment to get deposited on the sides of my river. So a flood is what happens when the capacity of my body of water is overwhelmed by the volume of water trying to fill it. And as that happens, any sediment that's in that water gets deposited on the side of my river. And it grows. Flood after flood after flood after flood. You get levees getting taller and taller and taller. And actually, every time it floods and adds to the height of that levee, it prevents future floods more effectively. The sides of my river get taller, causing less and less flooding as time goes on. We've learned from this, we can make our own levees. I'll show you those in a little bit. Okay? Huh?
I don't like that.
Okay, so again, a flood is what happens when your capacity is overwhelmed by the volume of water trying to fill it, okay? So regional floods happen generally when you have a lot of rainfall. That rainfall has to flow somewhere, and so it pushes through your area, overwhelming your local rivers, reservoirs, lakes, etc. This can also happen when you have a normal amount of rainfall, but a heavy amount of snow melting. So can anyone tell me why there might be a lot of flooding as a result of excessive snow melt these days? What could cause that? A higher than normal amount of snow and ice melting. Climate change, right? We're on an upward spike in temperature, global temperature, okay? Worldwide, temperatures are spiking. We're losing more ice in Antarctica. We're losing more ice in the Arctic. We're losing more ice on our mountaintops. Our glaciers are pretty much all melting. I think there's only 2 or 3 glaciers in the world that are actually growing right now. The rest are actively melting.
Texas got snow that stayed for more than 24 hours.
Well, yes, but that's a seasonal thing, not a long-term shift. Okay, and so people will try and say that. They'll be like, it's global warming, but we lost power because of a snow in Texas. I'm just like, that has nothing to do with long-term trends. Those are people complaining and whining because they don't like it when people talk about global warming. But here's the thing when it comes to global warming, and I'll stand on a soapbox here for a second. Hold on, all right, I'm on my soapbox now, okay? Global warming is happening whether people like it or not. Here's the thing, though. We didn't start it. That's where people are losing the narrative, okay? They're trying to use it for political leverage. Humanity did not start global warming. It started 12,500 years ago at the end of the last ice age. What do you call it when you leave an ice age? Except global warming, right? That happened before we were doing anything other than building fires. We did not build enough fires to start global warming and end an ice age. It happened on its own. We've been in an upward trend of warming ever since then. However, our contributions through, say, the expellation of greenhouse gases, through the use of hydrocarbons like gasoline and coal, they have significantly added to the rate at which that heat increases. This will be the hottest heat trend that Earth has had in quite a while. Not the hottest in history, mind you, but the hottest it's gotten this quickly in a long time because of our contributions. Okay? That is where the narrative stops. Not global warming is our fault. The severity of it is going to be on us, though. Okay? Hope that clears it up a little bit. We will talk about this concept a little bit more later on in the class. Okay? Stepping off my soapbox. Okay. Flash flooding is what happens when you get excessive amounts of water in places that are not geologically capable of containing it. So, say a place like, Odessa, Texas, with a lot of clay near the surface. Clay doesn't let the water soak in very well, right? So what happens when we get a heavy rainfall? We get a flood. Right. The water can't sink in very quickly, so it runs over the surface and going downhill. That's where we get our flooding, okay? That, and we have a heck of a lot of bad drainage systems here, which I guess this is kind of another soapbox moment, but people in Odessa will complain their faces off the minute anyone in government suggests a tax. But then they will also complain their faces off at our terrible drainage systems.
I love seeing the TikToks every time it doesn't floods.
Right. I used to live on Eisenhower Road, just 5 blocks down from the college. And every time it rained, my street had 2.5 feet of water in it. I wasn't able to leave my house to come to work. And that was a really wet year, that year that I lived there.
Since we moved here, both times that it's flooded, or the few times that it's flooded like that bad, we somehow were like out of town
No,
every time.
lucky.
You know?
Lucky. I've had my house flood. It's bad. And everyone complains about how bad the flooding is, but then when the city or the county try to put together a tax, say, like, hey, guys, give us 50 cents a year. If everyone does that, we can improve our drainage systems. People say, no more taxes! And then they'll complain the next time it rains, and they flood. But that's people for you. Okay. So then we have ice jam floods. What happens here is when your winter is over, and your ice that's been on top of your lakes and reservoirs and such begins to melt, and the chunks of ice flow downhill with the water, but then at some narrow part of the river, they jam it up, and the water starts building up behind this ice jam. And then eventually it gets hot enough that the ice melts away, releasing all that water at once, creating what is called an ice jam flood. And then you can have floods that come from the result of dam failure. Our artificial dams do not fail that often, but they have been known to. If you ever want to look up some pretty spectacular dam failure footage, look up the Grand Teton Dam failure. It was a pretty bad one, flooded a whole bunch of towns, created a lot of destruction. So how do we control these floods? Well, we've got artificial levees. This is an artificial levee here. Basically learning from looking at the naturally occurring levees that built up on the side of river systems, we can build these to contain some of the more mild flooding effects. They work sometimes. If you've ever been to New Orleans, any of you guys ever been to New Orleans? Okay. Almost the entire city of New Orleans is below sea level. Like 6 to 8 feet below sea level, okay? Which means that if there's ever a hurricane that rolls through, which does all the time, it will flood the entire city. And they try and stop it by the use of these levees, and those levees fail half the time. And then the city floods, and there's billions of dollars in damage. And then we can have flood control dams. These are dams which are not always filled with water, but are there to prevent the consistent flooding of communities and agricultural areas downstream. Their entire mission is, whenever the snow melts up here, to keep it from flooding down into those areas. It's there as a wall to contain that flood, and it fills up, this dam fills up with water, and they slowly release it over the course of the year to contribute to the communities and agriculture downstream. Okay? Then there's channelization. As a river is flowing downstream, it carries with it a whole bunch of sediment. We already talked about that, right? All that sediment fills in space at the bottom of my river. How do I make it so that my river can contain more water? I take out the sediment. This is channelization, the removal of sediment from my channel to accommodate space for more water to flow. Okay, if more water can fit in there, there's less likelihood that it's going to flood. Okay, any questions about running water? We're almost to the end, folks. Bear with me. Naomi, what did the green grape say to the purple grape? What did the green grape say to the purple grape? Breathe!
I can't. I have allergies.
Yeah, is it a good one? Is that a good one? Yeah? No? All right.
I'm too tired.
You're too tired?
Yeah.
Oh, man.
Didn't get
Trying to wake you up.
Nah.
No? Didn't work? All right. Why can't a T-Rex sell rifles?
Oh, here we go.
He's a small arms dealer. There's
That
the
one-
but
that one I like.
Okay, all right. Okay, let's talk about groundwater for a little bit, okay? Contrary to popular belief, there are no actual rivers of water underground. That's not how groundwater works. It still surprises me to this day how many people still think that. I don't I can't imagine it's taught like that in grade school, but maybe people just assume it. It is?
Well, kind of, sort of. They don't say it, from what I remember, they don't say it directly, but they kind of imply it.
They don't not say it.
Right, they imply it.
Got it. Got it. There are no rivers of water underground, people. Groundwater occupies a different kind of space as it flows underground, and I will get there in a second. But I had in my class a few years ago, I want to say coming up on maybe even 4 years ago now. Gosh, wow. Ouch. A lady in my class whose father had made a career, a very successful career, out of being what is called a dowser. Do you know what that is? A dowser.
Mario.
No, it's Bowser.
I assume it has something to do with the oil field.
No, actually, a dowser is someone who claims to have the ability, when they hold two copper rods and bring them close together, they claim to feel where there is water flowing underground.
Oh, like in the movies.
Yeah.
People that are like, I can smell glaciers and icebergs.
Crazy people.
Not crazy, con men.
Con.
It's a con. It's a con because you know what? Water is everywhere underground. You drill down, you're going to hit water. But these people, for the longest time, would go around and be like, drill here, you'll get water. And then they would drill, but lo and behold, water, and people are like, oh, have my money. And then they would get a reputation, and other people would pay them a lot of money. So this guy made a big career out of it, and she insisted, no, my dad did this for so many years. And I'm like, yeah, and I know exactly how he got his money too. He was conning people, honey. Sorry. Right? There is no characteristic, there are no physics, there's nothing that could give anyone the ability, no matter what kind of metal you're holding, to determine whether or not there's water underground. And the likelihood of there being water in any one location is extremely high because you just need to drill down to it. It's there. Okay? Before I get to the point about water being underground, I just want to point out that groundwater made the vast majority of the unfrozen fresh water on our planet, right? So most of the groundwater that we use is for agriculture. That's about 66% of all groundwater is used for agriculture. So plants and animals and things like that. About 19% is for public supply. That's city water, okay? Now, this water underground, if it's not flowing through river systems or anything like that underground, how does it move through the ground? It moves through the rock through these things called pore spaces. A pore is a gap between one object and another. There are sedimentary rocks, quite a few sedimentary rocks, that have pore spaces. Sandstone is my favorite example. Sandstone has a ton of pore spaces. Matter of fact, most of the best oil and water reservoirs underground are in sandstones. Okay? So here's pore. This is a non-porous material. This is a porous material. Pore spaces are essential to hold fluids. When a material is pore space, it can hold fluids, but not transport them. Fluids cannot move from one pore to another, unless you also have permeability. Permeability is how interconnected those pores are. So I'm looking for layers of rock that are both porous and permeable, so that I can not only find a layer of rock that has water, but also be able to pull the water out of it. Same thing goes for oil too, by the way, okay? The study of groundwater is called hydrogeology. Now, hydrogeology studies surface water as well, but primarily they're concerned with sources and purity and protection of groundwater sources, okay? So, when you are a hydrogeologist, you are helping people figure out things like where to drill a well. And how do you know that? You need to find what is called the water table. The water table is the depth at which you need to go before you reach saturated rock. Rock that is just filled with water. So usually what you would do is you would find a local river or lake, because those usually sit at or near wherever the local water table is, because they all want to go to sea level, but in your local geographic area, the closest you can get is the water table, okay? So here is our water table down here. Pretty easy to drill a well to the water table around in this area, but what if you happen to live in some, I don't know, a highland, like a mountain range or something? You'd have to drill really deep to reach that water table. Instead of going for the main water table, what you'll usually do is try and find some local alternative, something that we call a perched water table. In the layers of rock in these mountain ranges, usually what they will do is look for some other layer of rock that is impermeable, does not allow the passage of fluids through it. Like this clay. This is a layer of clay in this example. We would call that an aquitard. It is preventing the movement of water any further below it. So any water that percolates down through this mountain cannot pass through that aquitard to join the main water table. It gets stuck on top of this. We call that a perched water table, and that's what most people in more mountainous areas will drill their wells to. Okay? Something like that. A spring is where water is seemingly coming out of the ground. These are springs right here. And this is where the mythos behind water must flow through the ground in a river comes from. What's actually happening here... Hello? You gonna let me go back? There we go. What's actually happening here is this is an aquitard where one end of it is exposed, and the pressure of all the rock on top of this perched water table is forcing water out of the rock here at the edge of this aquitard. And it's literally getting pressed out of the rock. I've gone to a spring just like this and crawled up into it and actually made my way through that sort of cave all the way to the rock wall at the back where the water is currently getting pushed out from. There's no river system. It's literally just rock, and you can put your hand against it and you can feel the water getting pushed out of the rock, seeping out of the rock onto your hand. That's all it is. That's all a spring is. There is no river system. Okay? So, normally when we drill a well, we poke our little straws down into the water table, just like that. But the water table is not typically under enough pressure on its own to force the water up that straw and into your sink. What you usually have to do when you have a well is attach some sort of pump to it. Okay? You ever seen these kind of pumps? That's the classic method. You're creating suction by doing that, which is forcing the water up the pipe from the ground and into your bucket or whatever you're filling. Okay? There are electric pumps as well, gasoline-powered pumps, right? But the best situation is the one that costs the least amount of energy, right? There is a situation where you can drill a well and not need to put any energy into the water coming up on its own. We call these artesian aquifers. This will happen where we have tilted layers of sedimentary rock, okay? So here I have a layer of rock that is impermeable. Water cannot pass through it. And then here is another layer of impermeable rock. Okay? And between these two layers of impermeable rock is porous permeable rock capable of holding water. Well, where these layers of rock are exposed here at the surface, water is filling in that porous permeable rock all the way deeper, 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 filling in this whole layer down there. Because it is capped on the top and bottom by impermeable rock, that water must stay in that layer. But it is constantly under pressure by the water filling it from up here. That pressure is essentially going to make an artificial water table right there. As far as the water down here underground is concerned, it should be up there because that's where it's getting filled from at the surface. So what happens if I drill my little straw down into that? That water's going to whoosh up out of that well, attempting to reach that artificial water table. Artesian aquifers are great. We love finding those because you can exploit the water as a resource with a minimum of energy expended to do so. Okay? Now we've actually learned from this. We have learned from this, and engineers created an object, a design, that can use this process to create water pressure for our houses. Do you know what that object is? What is this marvel of engineering?
Restate the question, please.
Huh?
Restate the question.
What object have we built that replicates this function to create an artificial water table and provide pressure to your homes?
Hold on. Pipes? Plumbing?
Water tanks.
Oh.
You ever wondered? Yeah, have you ever wondered why we have these big mushroom-shaped things to hold water in? Why don't we keep them in tanks underground? Wouldn't that be better?
No.
Why?
Gravity.
Gravity what? Yeah, gravity is absolutely a factor here, but what is happening? We are pumping water from our well up into this water tank. It's filling that water tank, and however high the water level in that tank is, when we pump that water or when we let gravity take that water back out, that water wants to be at this artificial water table up high. And so it's going to pop out of our sinks and our bathtubs and our showers and our garden hoses under pressure already because it is trying to reach that level, way up high in the atmosphere.
So then what if your water pressure sucks?
Water pressure can suck because of a low water tank level. Sometimes when there isn't enough water to go around, they can't even do that, right? Water pressure can suck because the well is not currently active. It can suck because whatever pump they're using to take it from the well and put it up there is not on. There's a number of reasons why that might happen. In my experience being here in Odessa, when we've had really bad droughts and they've had to ration water and water pressure has been poor, it's usually because they're more or less moderating how much water people can have. Because when you say, guys, drought, don't use as much water, a lot of people are still going to use as much water as they want. So how do you control that? You cut the pressure so they can't. Right? Sucks to try and flush your toilet. It'll work, but you sure can't have a nice shower, and you sure can't water your plants, and you can't do any of that, because when it comes right down to it, only life essential functions are required for that water in the time of drought.
So when they tell you can water your grass from this hour to this hour, because that's when they have the pressure?
That's usually when they'll have the pressure on, yeah. Yep. Okay. Speaking of things like drought, let's talk about the environmental importance of something like groundwater. Groundwater is what I call a non-renewable resource. I mean, technically it is renewable. Technically, oil is renewable. Most people don't consider it as such. It takes millions of years to make more oil, but it is technically renewable on the geologic timescale. Water is absolutely renewable. Groundwater is renewable, but not as it matters to you and me in the way that we use it right now in our society. We are literally pulling groundwater at twice the rate it recharges. It's not sustainable. This is the High Plains Aquifer. We live down here at the bottom end of it, but it goes all the way up to South Dakota. Everywhere you see that is red, the water table dropped more than 150 feet. Everywhere that's yellow or yellowish, it's dropped 50 feet. Everywhere you see that is white, it's dropped at least 20 feet, 20 to 25 feet. And this map is about 15 years old. It's gotten worse. Okay. During the summer, when I don't have all these classes to teach, I usually teach at least one online class at a time during the summer. But I also do landscaping. Okay, I work for a landscaping company that my friend owns. We install sod and astroturf, and we cut bushes, and we do all that stuff. I've done this for about 4 years now. Every year, more and more people are paying us to put in artificial turf because there isn't enough water to water their lawns. I see more and more wells run dry every single year. Why? Because what happens to our water table as we pull more water from it? If I have a well that's drilled to 100 feet, but my water table drops 100 feet, that well runs dry. What are my options? Drill a new well or make the other one deeper. Both are expensive, but possible. I can do that. It'll work for a while. But what's going to keep happening to my water table? And then what happens when that well runs dry again? Even more money. Way more money. The deeper you go, the more expensive it gets.
Especially if you need different equipment because you reach a certain depth.
Yeah, exactly. So eventually, it's a losing game no matter what. Most of our water that we have here in Odessa doesn't even come from Odessa. Did you know that? We have to pay other cities for most of our water because we do not have enough water here locally to sustain our population.
I mean, it makes sense because doesn't our water also suck butt?
Our water's not great. Neither is the water we bring in. It's technically perfectly fine to drink. I wouldn't drink it untreated, though. You'll probably get kidney stones.
Oh.
Huh? Yeah, it's not great. It's not great. Okay, so that's one problem, right? We are losing this water. It's not good, not sustainable. Recall how I told you that this water occupies pore spaces in the rock. What happens when I remove the water from that pore space? What was once filled with water is now filled with air.
Pressure?
That pressure is going to cause these pore spaces to collapse. My layers of rock compress.
So it's
There we go.
no longer permeable.
It's no longer permeable, can't store stuff in it. But as it collapses, eventually that compression is going to make its way to the surface. And as my layers of rock underground are compressing, I'm going to end up getting holes. And in sinkholes. I'm going to get entire areas that collapse a little bit into the ground. This is called land subsidence. That is a side effect of withdrawing too many fluids from the ground. This occurs for both oil and water. Okay? There's actually, so this lab I've been working with, that I did this event with, that I've been doing some seismic studies with, we've been contemplating maybe doing a land subsidence study here in the Permian Basin, because we've been pulling oil and water out of the ground here for more than 100 years. What has the effect been for the subsidence of the land in the area? No one's really done a study on it, as far as we can tell. It would be interesting to figure that out. And then there's the contamination. Contamination of groundwater is a big issue. Why? Because we drink it. You don't want it to get contaminated. Okay? I recall hearing stories of people, laundromats, dumping their chemicals in their backyard for 20 years, only to find people in their community getting sick because those chemicals had gradually worked their way down into the groundwater, and now people were drinking it. Exactly. Fertilizers, pesticides, they can make their way into the groundwater system. People go to prison for that because you are contaminating a water source, which is a precious resource. Okay? Yep. When this groundwater gets superheated by usually the presence of magma, it turns to steam and comes up and falls back down and comes up and falls back down. Yeah.
Yellowstone?
Yeah, those are called geysers. Old Faithful in Yellowstone is an example of that. You can actually harness this method. This is called geothermal or hydrothermal energy. Okay? You can harness that to generate electricity. If you can capture that naturally heated water turned into steam and use it to turn a turbine, you're doing the same thing a coal power plant or a nuclear power plant does at zero cost to yourself. This is what they do in Iceland. This is a geothermal, hydrothermal power plant. Notice how small all these buildings are? There's nowhere there that is burning coal. There is no nuclear component here. They are not needing to generate any energy of any kind to turn water into steam. All they do is have buildings for capturing that steam and using it to turn a turbine. Because it's naturally coming out of the ground, because the groundwater is naturally turning into steam. Very efficient, very green source of energy. Okay. And then finally, this last slide, these are some examples of some of that ground subsidence, the sinkholes that can occur as your groundwater is dissolving spaces underground or those porous spaces are collapsing in on themselves. When it happens out in the middle of a sheep field, no one really cares. But if it happens under your house, all of a sudden it becomes a whole nother issue, right? Something to pay attention to, something to care about. Which is why we would hate to see it happen out here in our community. Okay, any questions about today's lecture? I know it went really long. We started 40 minutes late because of the technical issues. No questions?
We started 40 minutes late.
We did.
That's crazy. I didn't even notice because I was already working.
Yep, no worries. Okay, I'm going to end the recording here, and you guys have like 20 minutes for lab time.
Oh, well, good thing I was already doing my lab. So.
Yeah, good thing.